Optoelectronic devices are electrical to optical or optical to electrical transducers or devices. These are some optoelectronic devices. The first one, LED, which was discovered in the year 1904. Before 1904, the only non-semiconductor device was the silicon carbide point contact rectifier. Needless to say, the light emission from such a diode was very small. When LED was discovered in the year 1904, the light emission from LED attracted the interest of researchers all over the world. In a junction LED, the light is emitted by the process called injection luminescence or electroluminescence. So LED emits light by the process called electroluminescence. In an electroluminescent process, a very large population of electrons are injected into the normally empty conduction band, and with a small forward bias. And these electrons will recombine with the holes in the valence band, and light is emitted by the process of spontaneous emission, which is very different from stimulated emission. The spontaneous emission process requires a very small forward bias. So LED operates with very low current densities rather than lasers. The light emitted from an LED are of random phases. So LED is an incoherent source of light. LED is an incoherent source of light. But LED can support many optical modes. So it can be used in sources with multi-mode optical fibers. That's an advantage. It can support many optical modes. So can be used in optical fiber communications. Now we can look more into the electroluminescent process. In an LED, the input electrical energy is converted into output optical radiation in the visible or infrared range, depending on the type of the material. Depending on the type of the semiconductor material, the conversion happens. Now, the electroluminescent process takes place in two steps. The first one, the energy carriers of near band gap are injected into the highest state, which is greater than the equilibrium states. The second one, after staying a lifetime in the excited state, the electrons or the energy carriers come back into the lower state and light is emitted. So these two are the important steps with which the energy conversion in an LED happens. So this diagram represents the energy conversion and the spontaneous emission process in an LED. LED is usually forward biased. It works under forward bias. This is the circuit symbol of an LED. The conventional diode symbol with an arrow represent the circuit symbol of light emitting diodes. When we give a forward bias to the PN junction LED, the minority carriers are generated on both sides of the PN junction, and these minority carriers diffuse through the PN junction and will recombine with the majority carriers, and light is emitted. And here you can see the electrons, a very large population of electrons in the conduction band. This will go for spontaneous emission process and will recombine with the holes in the valence band, and light is emitted. The emitted radiation is having an energy equal to the band gap energy. The band gap energy is given by h nu. H is Planck's constant. Nu is the frequency of the emitted radiation. We know that nu is c by lambda. Lambda is equal to hc divided by Eg, where Eg is the band gap energy of the semiconductor material. Here H and C are constants, so the wavelength of emission or the color of the LED depends on the band gap energy of the material. The band gap of semiconductor materials used for the construction of LED should have a very wide band gap. Then only the light can escape from LED. In a conventional semiconductor diode, the band gap is narrow, so that the light emitted, even if there is some light emission, that light will get absorbed by the material itself. In an LED material, the band gap is very wide, so light can escape. So that is why LED is usually encapsulated in a transparent cover for the light emission. Now, there are different color LEDs. As you have seen here, there is a white LED. The white color is produced by phosphor conversion or RGB system or hybrid conversion, etc. The red and green LEDs have been known to us for 3 decades. The blue LED was a little bit difficult to construct, but that was also possible. The light emission from blue LED can be used for the generation of red and green light. Some of the examples for LED materials, for example, for violet, blue LEDs, for the construction of those colored LEDs, we use indium gallium phosphide. And for red and orange or yellow LEDs, we use aluminium gallium indium phosphide. So there are several other examples for LED materials. Nowadays, OLEDs, or organic LEDs, and PLEDs, polymer LEDs, are also common. And a new advancement in the LED technology is QLEDs. QLEDs are quantum dot LEDs. In a quantum dot LED, we use a quantum dot layer in between the P and N type of material. And the electron hole recombination happens in the quantum dot layer and light is emitted. The quantum dot LED has several advantages, like it is more reliable. It can be tunable over the entire visible range. So lots of advantages and applications are there for QLEDs. Now the uses and advantages of LEDs. As you can see in the slide, LEDs are used for signals, traffic signals, LED TV, digital display, for example in the case of the backlights and indicator lights of smartphones or tablets phones, and also in the headlights and indicator lights of motor vehicles. LED is used in burglar alarms. It can be used for high energy applications, high power applications. Suppose if we use an array of LEDs, we can use it for high power applications. So there are several uses for LEDs. Now, when we come to the advantage, LED is a green energy source, of course, and moreover, it has low power consumption. It can be used with low cost, and so several advantages and benefits are there for LED. So that's all about LED. Thank you.